Hello dear friends, welcome to the lecture of partial differential equations. We are studying partial differential equations, nonlinear partial differential equations of order 1. Last time we have studied JACOBI'S method, that is general method to solve PDE of nonlinear PDE of order 1. JACOBI'S method involves equations having two independent variable and one dependent variable. That means equation of the type we have studied x, y, z and p and q is equal to 0, and here x and y are independent variable, z is dependent variable. We have studied and for that purpose we have obtained another relation capital F in terms of the same variables. Then by using the JACOBI'S auxiliary equations, so we have obtained the values of p and q, and these values of p and q are then put in the differential of z, that is dz, which is p dx plus q dy, and on integration we get the required solution. Now what is the change here is, instead of two independent variable we will be having more than two, means 3 or more than 3 variables, and in that case the function can be written as instead of xy we will write the variables, independent variables, as x1, x2, x3, and corresponding derivatives of partial derivatives of z with respect to x1, x2, x3 as p1, p2, p3. So this will be the equation in terms of 3 variables. And now to find the solution for this PDE, again we require the values of p1, p2, p3, and then we will have to use that values in the total differential of z. And for that we know that there are 3 unknowns, means we require 3 equations. Here there are 2 unknowns p and q. To find p and q we have used these 2 relations, given function, given equation, and additional relation that we have to assume. So here likewise to the JACOBI'S method. So this we have done in JACOBI'S method. And in this now JACOBI'S method we are going to do we are going to consider this type of equations, and therefore there will require 2 additional relations, and we will denote these 2 relations as f1 of the same variable, say x1, x2, x3, and p1, p2, p3, and instead of 0 it may be considered as c1. And second relation we will consider as f2, which is of the same variables, is equal to c2. And from these 3 relations we shall obtain the values of p1, p2, p3. And here what will be dz? Dz here will be p1 dx1 plus p2 dx2 plus p3 dx3. And what is the p1 is partial derivative of z with respect to x1. Instead of xy, here the variables are 3, and we are considering these variables as x1, x2 and x3. So that is the change we are having in JACOBI'S method and JACOBI'S method. So we shall start the method. Consider a PDE. F of, instead of xy we have to consider x1, x2, x3, p1, p2, p3 is equal to 0. We suppose that is 1, where x1, x2, x3 are independent variables. Z is dependent. Z is dependent variable, and we have the partial derivatives of z with respect to x, with respect to x1, x2 and x3, and that we will denote by pi. And pi is equal to dou z divided by, or dou z by dou xi. I takes values 1, 2, Now that will be P1. P1 will be dou z by dou x1. P2 will be dou z by dou x2, partial derivative of z with respect to x2, and likewise P3 is partial derivative of z with respect to x3. So this is the notation that we are following for this equation having three independent variables. Now we assume two algebraic relations f1 and f2. We take two additional relations as, say, f1 x1 x2 x3. f1 of this is equal to some constant c1, and we shall suppose this as second, and f2 as capital F2 having the same variables. Now here Pi is dou z by dou xi. We have to solve these equations. We solve 1, 2, 3 and obtain the values of P1, P2, P3. So solving, we will write briefly the procedure, what we are going to do, and then we will obtain actual steps in the method. So solving 1, 2, 3. We get the values of P1, P2, P3. And then we put this in. Put these in. dz is equal to P1 dx1 plus P2 dx2 plus P3 dx3. Where what is P1, P2 is to be clear. P1 we have written here. Partial derivative of z with respect to x1, partial derivative of z with respect to x2, P2, and P3 is partial derivative of z with respect to x3. So also this integrating this equation, integrating dz, we get the required solution. Integrating, we get the required complete integral. We get the complete integral. And here one thing is to be noted, where we have, what about dou P1 by dou x2 is equal to dou P2 by dou x1, and dou P2 by dou x3 is equal to dou P3 by dou x2, and that is partial derivative. These are partial derivatives. P3 by x1, and that will be dou P1 by dou x3. Now it is easy to verify. What is the P1? P1 is this one. See, dou z by dou x1, and dou of dou by dou x2 of dou z by dou x1 will be dou 2x. See, for this that will be dou 2z by dou x2 dou x1. And what is the right side? That is dou by dou x1. What is P2? This is dou z by dou x2, and therefore the right side is of this relation is, and that is dou x1 dou x2. And we have this, the property of second order partial derivative. The second order partial derivative in general is this equal, because this equation is integrable. P1, P2, P3 are integrable, and therefore these partial derivatives are the same. Dou 2z by dou x2 dou x1 is equal to dou 2z by dou x1 dou x2. Here it is z is differentiated partially with respect to x1 then with respect to x2, and here first it is differentiated with respect to x2 and then with respect to x1. So this is the same, and you may verify the only the suffixes are interchanged. P1 2, here 2 1, 2 3 3 2, and so on. So thus this relation between partial derivatives hold, and we shall assume this as a say an equation denoted by star. Now what we shall do is to obtain the auxiliary equations to find P1, P2, P3, and for that purpose we differentiate 1 and 2 partially with respect to first variable x1. So that we will do now. So differentiating 1, differentiating 1 and 3 partially with respect to x1, we get. Now see how to differentiate 1 partially with respect to x1. So that will be dou f by dou x1. First variable is, we have to use the chain rule, dou f by dou x1 plus, and partial derivative of this f with respect to x1 when we are getting x2 and x3 are to be treated as constant. So x1, x2, x3, these are the only independent variables, and so therefore when we differentiate partially with respect to x1, x2, x3 will be constant. Similarly, when we differentiate partially with respect to x2, then x1, x3 will remain constant, and so this happens between these independent variables, and we have to take remember we have to take the derivative of p1, p2, p3. So therefore it is the partial derivative of f with respect to x1 is dou f by dou x1 plus, next we have to go to p1, and first see f is function of p1, so it will be partial derivative of f with respect to p1. So the derivatives with respect to x2, x3 will be 0 because x2, x3 derivative of x2, x3 will be 0 with respect to x1 because x2, x3 are considered as constant when we partially differentiate with respect to x1. So therefore we have to consider the partial derivative of f with respect to p1 and into, but we are differentiating with respect to x1. So partial derivative of p1 with respect to x1. So this much is the derivative with respect to this corresponding to this variable p1. Similarly, the next partial derivative of f with respect to p2. This is small f. Small and capital notation we have to follow correctly. Dou f by dou p2 into dou p2 partial derivative of p2 with respect to x1 plus, and next will be partial derivative of f with respect to p3 into partial derivative of p3 with respect to x1 is equal to 0. Now we shall suppose this relation as 4. See, we have differentiated 1 partially with respect to x1. You observe this step carefully, and if you understand this, then the remaining part will be as usual. Now further, so we have written 1 and 3. Now 1 we have differentiated with respect to x1. Similarly, 2 we should differentiate with respect to x1. So what is the change here is in place of small f there is capital F1. So that is the only change for this second step, and that will be dou f. So this is, and dou capital F1 by dou x1 plus dou capital F1 by dou p1 into dou p1 by dou x1, and so on. Only small f is replaced by capital F1, and that is this. We are using the chain rule of partial differentiation. And this is our fifth equation. Now what we shall do is we eliminate this dou p1 by dou x1 from 4 and 5. See, this is to be eliminated. This term is to be eliminated. And to eliminate, or this is the term to be eliminated. And for eliminating this, we use the procedure of elimination. Now, what is the usual? When we solve algebraic equation, we use the elimination procedure. That means if this type of equation is there, say 2x plus 3y and plus etc. or is equal to a constant, say 5, and another equation can be considered as say 3x minus 2y is equal to 7. So when we want to eliminate this x or y, what we should do, their coefficients should be made equal. And to make the coefficient equal, for suppose we want to eliminate this y, so we multiply this first equation by minus 2, multiply the second by 3, and then we add it. So if there is negative sign, opposite signs, then we add it. Or if you multiply this, if it is having the same sign, multiply this first equation by 2. We multiply the second by 3 and then subtract. So this y term will be eliminated. Exactly same procedure we are going to use to eliminate this term dou p1 by dou x1. And that means we multiply the first term by fourth equation by this term, and we multiply the fifth equation by this term. So that means this term is to be multiplied for the lower equation, and this term will get multiplied to the upper equation, fourth equation. So that is the procedure of elimination. So eliminating dou p1 by dou x1. So we will get from 4 and 5. Now remember to multiply this term to the upper equation, fourth equation, multiply fifth equation by this term and subtract. So that is the elimination procedure, and we will do it directly. So we have the first term dou f by dou x1, and this is to be multiplied by dou f1 by dou p1 minus, and now the lower term is, see, dou f1 by dou x1, and that is to be multiplied by this. So that the term, this we are multiplying below, dou f by dou p1 and into dou f1 by dou x1. So this is the term, original term. So this cross multiplication we have done. So first is multiplied by this, the product of these two is here, and then the product of these two is here, their subtraction is there. And now second term obviously becomes 0, eliminates, because the term becomes same, product of these two into this, and again product of these two into this, subtraction of that is 0. Now we go to the next term, and again you see this is to be multiplied by dou f1 by dou p1. We have done this procedure in Charpit's method also. So this we will put this in one bracket plus. Now see this dou f by dou p2 and is multiplied by dou f1 by dou p1 minus, and the cross product of this, and now the cross product of this. So dou f by dou p1. A small f term we will write first, then we will write capital F term. So dou f1 by dou p2, and that is multiplied by dou, this is common, dou p2 by dou x1. It is common. This term is common. See, this is the common term, and then there is a cross multiplication of this. So this common term we have written here, and it's only arithmetic part you can understand. Plus, now what about the next, or these two? So here this term dou p3 by dou x1 is common, and again there is cross multiplication of this. So that is dou f by dou p3 into dou f1 by dou p1 minus product of these two, and product of these two is dou f by dou p1 partial derivative we are saying like dou. So dou f by dou p1, and this is dou f1 by dou p3, and this is dou p3 by dou x1, and the right side is 0. So this equation we shall assume as 6. Though the equation is somewhat lengthy, it is not difficult to understand it. And thus, so what we have done is we have differentiated 1 and 3, or 1 and 2, not 3. So there must be this correction. So differentiating 1 and 2, first and second. Here small f and capital F1. Partially with respect to x1, first variable. We obtained this equation. Now similarly, differentiating say 1 and 3 partially with respect to x1, and again we will get again 2 and 3 partially with respect to x1. We will get the other variables. So other equations we will get here likewise. Similarly, eliminating. So we can write as similarly eliminating dou p2 by dou x2, we will get the other equations, or we will write directly the equations. Now how the equations are to be considered written, as you see, we will similarly eliminating, we will consider the same pair, not the different. See, 1 and 2 again. So what we have done, 1 and 2 we have differentiated partially with respect to x1. Now 1 and 2 we will differentiate partially with respect to x2, second variable. And again we will get the next equation. And then we differentiate 1 and 2 again partially with respect to x3. So I shall write differentiating 1 and 2 partially with respect to x1 and x2 we get. Now I think this is clear, so I shall remove it, and we will keep this equation only. So further, differentiating 1, 2 partially with respect to x2 and x3. x2 and x3 we get. So this is the resulting equation we have obtained by differentiating with respect to x1. Now when we differentiate 1 and 2 with respect to x2, which is the equation that we shall get? Observing this equation we shall write the new equation. So we are here, differentiation with respect to x1 results this equation. Now differentiation with respect to x2 will result the equation dou f by dou x1 will be now x2. So in place of x1 p1 we have to increase the suffix, that is to be x2 p2, and again we have to interchange p2 and p1. So p2 p1 is to be written as p1 p2. So that is the change to be done to write the next equation. You can verify doing the same procedure, and therefore first it will be dou f by dou x2 and dou capital F1 by dou p2 minus this is dou f by dou p2. p1 becomes p2, x1 becomes x2. No change in f and f1 because we are fixing the same f and f1, 1 and 2 only we are differentiating with respect to x2, and then with respect to x3. So this is dou f by dou p2, dou f1 by dou x2, first equation, plus the second one will be see dou f by dou p2 will be now p1. p2 will change to p1, p1 will change to p2, and this is p1, and this will be dou f1 by dou p2 minus dou f by dou P2, and this is dou capital F1 by dou P1. This is multiplied by dou P2 by dou P2 will be now dou P1 by dou X2. So these are the changes to be done, and this, and next plus the next will be this one, dou F by dou P3. There is no change in P3, only 1 2 and 2 1 changes. So dou F by dou P3, this is dou F1 by dou P2. P1 changes to P2, see, and it is to be X1 P1. X1 P1 changes to X2 P2. P1 changes to P2, X1 changes to X2. So that is the change. And here P1, P2 are interchanged. So next is minus, this is dou F by dou P2, dou capital F1 by dou P3 as it is, and this is dou P3 by dou X2 is equal to 0, and this will be our equation number 7. Now the next is equation, after equation 7 we shall have to write equation number 8, eliminating x3 from these two. So I shall write here further after this step, and what is the next equation is, so from this we can observe x2 P2, x2 and P2 will be increased to x3 and P3, suffixes will increase by 1, and similar thing happen here. So P1 P2 and then P2 P3 are to be changed. P2 P3 are to be changed as, say, P3 P2. In place of P2 we have to write P3, in place of P3 we have to write P2. So these are the changes to be remembered, and we write the next equation. So that will be dou F by dou X3, dou F1 by dou P3 minus dou F by dou P3, dou capital F1 by dou X3 plus, and next will be dou F1 by dou P1, no change in P1, this is small f, and next is capital F1, capital F1, dou F1 by dou P2, P2 becomes P3 minus, next is dou F by dou P2, P2 is now P3, P2 is P3, and P1 no change. So or we may write here P1 remains P1, here P3 remains P3. To write the next equations we are doing these cyclic changes, and that can be verified by independently, and this is dou F by dou P3, dou F1 by dou P1 no change, dou F1 by dou P1 no change, and dou P1 no change, dou X2, X2 becomes X3, and plus the next step, next term, that is dou F by dou P3, P3 becomes P2, see, P3 is P2, so that is dou F by dou P2, and dou F1 by dou P2, P2 is now P3 minus dou F by dou P2 means dou P3, and dou F1 by capital F1, dou capital F1 by dou P3, P3 is P2. This is multiplied by dou P3, P3 is P2, and by dou X2, X2 is X3 is equal to 0. and this is our equation number 8. So this much is the part to be understood carefully, how the equations are written. Only we have differentiated 1 and 2, not yet third equation is considered. 1 and 2, first we have differentiated with respect to x1, and then we have obtained equation 6. And similarly we should have, so here may be written similarly differentiating 1 and 2 partially with respect to x2. So this is with respect to x2, gives this relation. With respect to x1 gives 6, with respect to x2 gives 7, and with respect to x3 gives 8. So these equations we have obtained. Now what we shall do is we add these 6, 7 and 8. Adding 6, 7 and 8. 8 and noting and or using star. What is written in star we have there, we get. We have written in star as dou P1, see this relation, this one, dou P2 by dou x1 is same as dou P1 by dou x2. That is star equations we have. And so star, or otherwise I shall write the same equations here as dou P1 by dou x2 is equal to dou P2 by dou x1, etc. These are star equations. And what we will get is the addition of these brackets. First, there are 3 terms in each equation. First bracket, second, third. And here also this first, second and third, and so on. So in addition, what we will do is we will add this term. So these terms will get added. That means the first term from the sixth equation, then the second term from the 7th equation, and then the first term from the 7th equation and first term from the 8th equation. That these terms will get added. And what happens to the remaining terms? Now you see, what is this term? This is dou f by dou P2, dou f1 by dou P1, etc. And this is dou P2 by dou x1. But dou P2 by dou x1 is same as dou P1 by dou x2. And where is dou P1 by dou x2? That we will see. Dou P1 by dou x2, you see. These two terms are equal. Dou P1. So this partial derivative, second order partial derivative, we have written that in star equation. This is actually second order derivative of z with respect to x1, x2. And that is also the same, second order derivative of z with respect to x1, x2. So 1, 2 and 2, 1 are interchanged, it remains the same. And thus these two are equal. And if these two are equal, and if we add it, then what happens, you see, this term is dou f by dou P2 and dou f1 by dou P1. And you may observe, this term is exactly the same with opposite sign, and these two terms cancel. And similarly, this is dou f by dou P1 and dou capital F1 by dou P2, positive, negative, so this cancels, and that means these two terms cancel. And next, similarly, what we will have is this term dou P3 by dou x1. Now this is over, Now we will consider dou P3 by dou x1. So this is exactly same as dou P1 by dou x3. So where is the term dou P1 by dou x3? 1 and 2 are interchanged, and you may observe this is the same. See, dou f by dou P1, dou f capital F1 by dou P3, positive, negative, and this is positive and this is negative. So these two terms cancel. And so this we have seen, these two cancels, these two terms cancel. Now these two terms cancel, and what remains is dou P2 by dou x1, dou P2 by dou x3, dou P2 by dou x3, and that so this is here. Now earlier these two terms cancel, and now we have seen this and this one cancel. Now dou P3 by dou x3 and dou p3 by dou x2. So these two terms will cancel. So you see, this is positive term and this is negative, equal and opposite. Similarly, this term is positive and this is negative. So this is also equal and opposite. In all, what we observe is that the remaining terms get cancelled and only the underlying term remains. So this term remains from 6th equation, this term remains from 7th equation, and this term remains from the 8th equation. All other are equal and opposite, and that gets cancelled. So therefore what we shall get is, we write, so using star we get, and I write the equation here, that as dou f by dou x1 into dou capital F1 by dou P1 minus this is the term from the first plus this is the term from the second, 7th, you see, dou f by dou x2 dou capital F1 by dou P2 minus dou f by dou P2 dou capital F1 by dou x2. So that remains from second and this remains from third. Plus is so this is P3x3. So thus this is the equation that we have obtained, and we suppose this as 9. Equations 9. These equations, so thus in all we have differentiated 1, 2 with respect to x1, x2, x3, and we have eliminated these terms dou p1 by dou x1, etc. We have obtained 6th, 7th, 8th. Adding these we get this one, and that can be written in brief notation, sigma notation, summation. So that is, so this can be written as summation I takes value 1 to 3. You see, it is 1, here the suffix is 2, and here the suffix is 3. So therefore in short we can write this as dou f by dou xi and dou capital F1 by dou pi minus dou f by dou pi dou capital F1 by dou xi. I takes value 1 to 3 and this is equal to 0. And likewise, similarly, eliminating x1, x2, x3 from the equation 1 and 3 and 2 and 3, we will get two more such relations. So what we have used here earlier is 1 and 2 we have used. 1 and 2 we have used, and now we will use 2 and 3, and then we will use, 1 and 3 we will use, and we will then use 2 and 3 to get two more such relations. So similarly, we will have eliminating, we have from 1 and 3, or we may write 1 comma 3 and 2 and 3, 2 comma 3. We have from 1, 3 and 2, 3. So what will be from 1, 3? What is the change? I taking value 1 to 3. From this, see, the 1 is small f. What is first equation? You see, the first equation is small f is equal to 0. So we have our starting equation, small f x1 x2 etc. This is 1. And what is second? f1. And what is third? f2. So from 1 and 2 we obtained this small f, capital F1, small f, capital F1, 1 and 2. Now from 1 and 3 will involve f and f2. So that means this will be dou f by dou xi, dou f2 by dou pi. In place of f1 we are using f2, f and f2. 1 and 3 minus dou f by dou pi, and this is dou f1 by dou f2, it is dou f2 by dou x is equal to 0, and this will be our next equation, that is 10th. 9 and this equation is the same, that is written in brief form, and what we will get another next equation is, and summation I takes value 1 to 3 dou f by, now you see 2 and 3. 2 and 3 means f1 f2 we have to use from 2 and 3. So in place of this f and f2 there will be capital F1 and capital F2. Dou xi, dou capital F2, dou pi minus dou capital F1, dou pi, dou capital F2, dou xi, and is equal to 0. So this is 11. So thus we have obtained equations 9, 10 and 11. 9 is the same in brief form, this one. So and from this 9, 10 and 11 we will get the value of f1 and f2. Solving this. So but before that we have to write the auxiliary equation. From 9 and 10 are Lagrange's equations. See, this is a Lagrange's equation or similar to Lagrange's equation. Now how to write the auxiliary equation for Lagrange's equation? Actually the Lagrange's equation we have studied is of this form. Say P, capital P small p, capital Q small q is equal to R. And there we have this as dx divided by p, auxiliary equation. Dx, actually this p means dou z by dou x. So this is p dou z by dou x plus q dou z by dou y, or minus r is equal to 0. And this gives the auxiliary equation as dx, this variable, differential, divided by p, dy divided by q, and equal to dz, this variable dz divided by r. So or this r is on the right side. So this is Lagrange's linear equations. Exactly similar type of equations are these. Equations 9 and 10 are Lagrange's auxiliary equations. Not auxiliary, but we can consider Lagrange's equations. And now we will write auxiliary equations from it. So therefore, from these, JACOBI'S auxiliary equations are JACOBI'S auxiliary equations are. Now you see how to write the JACOBI'S auxiliary equation. We may observe 9th. Here it is, see, this is dou P1. Dou P1 is the differential at the denominator, and this is to be considered at the numerator. Here this is dou x we have taken at numerator, and this suffix is written at the denominator. So if I write dou P1 at numerator, this will be at the denominator. So therefore the Jacobi's auxiliary equation from the first term is dP1, dou becomes d now. This dou x becomes dx, total differential, divided by the coefficient of this derivative term. And this coefficient is dou f by dou x1. So that will be dou f by dou x1 is equal to. The next we will write first the positive terms are this dou P2, and that is dP2 divided by, this is dou f by dou x2 and is equal to dP3. Go to next term, this one, dP3 divided by dou f by dou x3. So after these positive terms are considered, now we will consider this one as dou x1 means at here it is total dx1. Likewise this we are writing. So dx1 divided by negative of dou f by dou P1 and is equal to dx2 divided by next term to this here it is negative dou f by dou P2 and is equal to now dx3, last one dx3, and that is negative dou f by dou P3. So these are the Jacobi's auxiliary equations, or auxiliary equations in Jacobi's method, and we have to remember these equations for solving the problems. So we may suppose these equations as 12. Solving these, we get the values of F1 and F2. And solving these, we get, first we will get the value of P1, P2, etc. Solving 12, we get P1, P2, P3, etc. We get the values. Solving this 12 with not only isolated but solving 12 together with, we will consider solving 12 together with 1, 2, 3. We obtain the values of P1, P2 and P3. Then putting these values in, the differential of z, that is dz. dz is equal to, what is dz? P1 dx1. Actually, what is dz? Z is the function of three independent variables, and therefore it will be dou z by dou x1 dx1 plus dou z by dou x2 dx2 and plus dou z by dou x3 dx3. But what is this? This is P1, this is P2 and this is P3. So that is P1 dx1 plus P2 dx2 plus P3 dx3. Put these values in this dz. Integrating it, we get the required solution. Integrating this, we will get the required complete integral. Integral of original equation 1, that is f is equal to 0. And thus this is the Jacobi's method, which is used for equations involving 3 or more independent variables. We have considered the case of 3 variables x1, x2, x3. If there is one more variable x4, then this will be extended. That will be dp4 by dou f by dou x square etc. And here dx square divided by negative dou f by dou p3. And then we will solve this equation by grouping method or by using the method of using the properties of ratios. And then we will obtain the value of p1, p2, use these values of p1, p2 with 1, 2, 3 original equation and additional f1 and f2. Then get the values of p1, p2, p3, put the values of p1, p2, p3 in this relation dz, integrate this, we will get the required complete integral of the original equation. So this is what is the JACOBI'S method. You go through the method. The method is somewhat lengthy but not difficult to understand. Only we have used the elimination procedure, and for differentiation we have used the derivative of composite function. So problems on this method we will solve in our next lecture. Thank you.